Hi everybody, welcome to our next topic in grade 12 physics. So today what we're going to be looking at a little more detail are some ideas about collisions. So if you remember last time in our last video we learned about momentum conservation in one dimension, and we want to build on that today and look at some special cases of when momentum is conserved in 1D. So a couple things to recall before we get too far into this idea of collisions. Momentum, there's our definition, this idea of conservation of momentum right here. And I just want to quickly talk about those two different forms of conservation of momentum, because there's been a lot of issues some people have with how these things are expressed. And so maybe we should go back to the basic sort of idea like this. So this form of saying conservation of momentum says that the total momentum, so T being total, momentum before any sort of action is equal to the total momentum after that same action. The action could be a collision, an explosion, throwing something, but the total momentum before and after is the same. And these ones over here are the same sort of expression, just expressed in a different way. So this one on the bottom, saying total momentum is equal, or change in total momentum is equal to 0. And all that means is that the momentum before and after is the same, because I subtract them and I get 0. And this one right here is just saying any momentum object 1 gains is accounted for by the same amount of momentum being lost by object 2. Just quickly to point out, this one right here only applies for two object systems, where this one and this one are true for any single case in the entire universe that we know of. So momentum conservation in total, this one only being true for two objects, because I've only listed two objects. The next one in our expression for kinetic energy, again, something that hopefully you remember from before. All right, so with that in mind, what we do want to talk about today are types of collisions and some special cases of collisions. And there's actually kind of three things we can talk about. But before we do that, we want to go back and say we know a couple things. So we know that in every single interaction, every single collision, momentum and total energy are conserved. That's true in general. That momentum and energy is one of those quantities in the universe that happens to be conserved. And if we know more about the collision, we can actually make some conclusions about what else has happened to the energy. And specifically what we're going to look at today to help us is this idea of kinetic energy and the energy of motion. So the three kinds of momentum, the three kinds of momentum we want to talk about. Let me go back here, sorry guys. That's better. Are elastic, inelastic, and completely inelastic. So these are the three sorts of types or classes of collisions. And so we can look at what does this collision look like and what sort of information do we have about it. So we'll start with elastic. So any collision that's elastic, they bounce off each other at a very high speed. An example might be when you throw two superballs together. So what we can actually say about momentum and then energy, so notice momentum again is conserved. Momentum before is equal to momentum after. But something even more special about elastic collisions that separates them from the other kind is that kinetic energy is conserved. So the kinetic energy before the collision is the same as the kinetic energy afterwards. So what that means, no energy is lost to other forms. So the energy before they collide, or kinetic energy before they collide, is the same as the kinetic energy after they collide. I'll jump to the bottom one here. To completely inelastic. For a completely inelastic collision, notice again momentum is conserved, because that's true in general. But in this case, the kinetic energy after the collision is a minimum. So as much kinetic energy that could be removed from the system has been removed and converted to other forms. And the minimum energy we have is just governed by this idea that we still have to conserve momentum. Momentum conservation is always true, so we can't have that be violated. So what that what this always looks like for two objects when they collide completely inelastically is they stick together and travel together. So they're like one object after the collision. So throwing two balls of Play-Doh together, or two cars in a collision that stick together, that would be a completely inelastic collision. If it's just inelastic, all that means is the energy is actually, kinetic energy is lost during the collision. So some kinetic energy is transformed to other forms, and kinetic energy before the collision will be greater than the kinetic energy after the collision. But again, notice our still idea there that momentum conservation is true. So when you have this other information, like we have an elastic or a completely inelastic collision, we can actually make our life a lot easier. And so let's start by looking at a couple examples here. Those ideas in mind, let's take a look at a specific example here. So we have two identical pool balls, and they're going to collide in a head-on elastic collision. Before the collision, A is traveling to the right and B is stationary, and I want to know what are the velocities of the balls after the collision. So let's just start by drawing a picture of what's happening here. So here's ball A, and it's heading in, and it's going to strike ball B that is initially stationary. We want to know what happens to these balls after the collision. So again, to note here, this is an elastic collision, so it means along with momentum conservation, we can also be using kinetic energy conservation. So we actually have two ways to approach this, because it looks like at first glance that we don't have enough information, because all we know is the initial velocity of the ball coming in and the fact this one is stationary. But if we take a look at, again, setting up momentum and kinetic energy conservations, we should be able to come up with a way we can solve this problem. So we'll start by there's the momentum conservation idea, and over here I'll do the kinetic energy conservation idea. And again, notice this is the total momentum and total kinetic energies we're talking about here. And in our two-body system, that's going to be the momentum of A, momentum of B, and the kinetic energy of A, kinetic energy of B. And again, we want to figure out what's going to happen after these things collide with each other. We expect, again, that something's going to be traveling to the right, because the overall momentum beforehand is to the right, so the overall momentum afterwards should be to the right as well. So let's just go and set that up. So again, we have two objects, but notice initially B is at rest, so I can simplify that a little bit and just write mVA is equal to mVA prime plus mVB prime. All right, so there's our momentum conservation statements. And similarly, I can do the same thing for kinetic energy. Again, noticing that initially this first ball, B is at rest, so all of the kinetic energy to begin with is in ball A. And afterwards, we're not sure yet, but kinetic energy could be in ball A. Could be in ball A, here. So VA prime squared, or it could also be in ball B. So again, if we take a look at these two expressions, we have a couple things we do know and a couple things we don't know. We don't know the masses, but luckily they're identical pool balls, so all of these masses can cancel off. And that makes our life a little bit simpler. And while I'm at it, I'm going to also cancel off the halves over here on the energy side. And the things I don't know are VA prime and VB prime. So all I know right here now is VA and VA squared. So I have two equations with two things I don't know. So again, hopefully you remember your grade 10 math. What we can do is then solve these equations for one for the other and sub it into the other one. Little slight wrinkle here. This is the vector form, so the vectors are conserved. And over here, it's just the magnitudes or the speeds or the scalars. So we'll look at a little bit later on how we can handle this stuff when we look at two-dimensional conservation and two-dimensional collisions. But for right now, we're in luck that everything's happening in the same plane. Everything's happening in the left-right plane, because ball A is traveling to the right, so the initial momentum totally is in the right. So afterwards, the initial momentum, the momentum needs to be to the right as well. So we can actually simplify this a little bit and come up with, well, if it's a head-on elastic collision, the only force acting on B is to the right. So B is going to have to travel to the right at somewhat. And so I can actually drop these vector signs then. I can just say that the velocity, the speed of A is equal to the speed of A afterwards plus the speed of B afterwards. And again, I hope you can see why I can drop the vector signs here. Because we're traveling in one dimension, I don't have to worry about vectors, but we will talk about how to bring that in later. So if I sub that into this expression, so I'm going to have VA squared, so I'm just going to take this instead of the VA. And if you remember your binomial expansion, so I'm going to have VA prime squared plus 2 VA VB plus VB squared. So there is VA squared. That's the same thing as this is here then. And it's equal to VA prime squared plus VB prime squared. And again, I've got some terms that are in more than one spot. So I have a VA prime squared over here and over here. So they're gone. And I have a VB prime squared over here and over here. So what I'm left with now is that 2 VA VB, oops, I forgot my primes on these, prime and prime, has to be equal to 0. So we've done this math trick a couple times now, but I have two numbers, VA and VB, that multiply together to give 0. There is only two possible solutions in the entire universe that will work for this. So either VA prime is 0 or VB prime is 0. And that means that the final velocity of one of these balls has to be 0. There's no other solution that would make this work in one dimension. So if I look up here at the top, well, beforehand B was not moving and A was traveling. So that means that A must come to a stop and B must be traveling. So what that means is the solution I want that's going to solve the problem that I'm looking for this time is this guy here. VA prime is equal to 0. So we now know that one of the balls is not moving, the one that was initially coming in. And if we take it and sub it into one of our other equations up here, let's say this one right here, we know that VA prime is 0, so that means VB prime has to be equal to VA. So the initial velocity of A is equal to the final velocity of B. So that means our velocity of B is 10 meters per second to the right. So at first glance, again, this looks kind of strange. What this means is these balls have almost traded velocities. So A started at 10 meters per second. Oh, I don't know where 10 came from. Pardon me. Not 10 meters per second. 2.5. So ball A started at 2.5 meters per second, and ball B was at rest. And then afterwards, ball A is at rest, and ball B will be traveling off at 2.5 meters per second to the right. So it's almost like these balls have changed or traded momenta. So the momentum of A has gone to B, and the momentum of B has gone to A. And again, I imagine that if you've ever played pool, you might have had a shot like this where you smack the balls dead on, and one of the balls comes to a dead stop, and the other ball takes off at a high speed. So again, this is true in general. Again, we've made a couple simplifying assumptions here. Our masses were identical, so we can't always do that. And we've also said this is a completely head-on collision, which means there is no velocities up or down, or it's just left and right. So again, later on in class, we'll take a look at examples where it's not like that. All right, so let's move on to our next one then. Completely inelastic, and if you remember, what happens there is that the objects stick together. So there's a kind of diagram there to help you what that looks like, and our key piece of information we have to help us. And we have this idea, we've done questions like this already in class. Now we just have a name for it. We're going to call this completely inelastic collisions. So since we have already done a bunch of questions like this, I'm going to leave this one for you, and I'll tell you when I did this, I'm getting an initial velocity. So again, I'm getting for an answer for the initial velocity of ball B to be 3.9 meters per second to the left. And again, I'll leave that to you to verify that. Hopefully you can do that question, because again, we have done a bunch of these already. All right, so there's completely inelastic, and there's one more we have to deal with. And again, we've done ones like this before. This would be partially inelastic collisions, or we just call them inelastic collisions. And we really only have one piece of information to help us, and that's that idea's momentum is conserved. So we're going to need some more information to actually solve this problem. And so an example we've got here, we have these two asteroids in space. They're about the same mass, but B is slightly more massive, and they're traveling towards each other. Before the collision, they have these velocities, and I've told you the velocity of asteroid A after the collision. I want to know what is the velocity of B after the collision. So if we kind of set up our system here, we've got A, which has a mass of 800 kilograms, traveling towards B at 122 meters per second. And I have over here object B, which has a mass of 900 kilograms, and it's traveling at 68 meters per second. And then after the collision, I have A, oh, that's not the right number. Oh, let's fix that right now, guys. Sorry, that's not 85 meters a second. That's 25 meters a second. So afterwards, I have A traveling at 25. Oh my goodness, I made a lot of typos here. 25 meters per second to the left. Wow, okay, let me put that in my picture so it's easier to see. So what I'm saying here is then that A is now traveling at 25 meters per second this way, and I want to know what the heck is B doing. Which way is it going? I don't know at this point. It's going to be left or right, not up or down. Hopefully you can see that just from momentum conservation, but we're not sure which one it is now. So let's work through this and see if we can solve it. So all we're going to do is our same sort of thing here. We don't know anything about the potential or kinetic energy. All we have is the momentum before is equal to the momentum after. And so we have MAVA plus MBVB is equal to MAVA prime plus MBVB prime. Unfortunately, nothing goes to zero here and nothing really cancels out. So we're kind of stuck with this expression as it is. But we have every term we need except for VB prime. So it's just a matter of rearranging this equation for VB prime and solving. And so I'm getting VB prime equals MAVA plus MBVB prime. Oh, sorry, not prime. MBVB minus MAVA prime, all divided by MB. The only word of caution I have here for you here is you have to worry about the directionality. These are vectors, so positive versus negative. But when I do this, I'm getting that the velocity of B afterwards is 63 meters per second to the right. Okay, so I think that question makes sense there. Again, we've done questions like this. It's just now a matter we have a name for it. We call this inelastic collision. So that's it out of me today, guys. I've given you 2 problems here, actually 3, I guess, because you haven't done the other one yet, but 2 more here you can try. I'm not going to tell you the answers right now. I'll ask for your answers in class tomorrow, and then we'll vote on these and see if how you guys did. So hopefully everybody has a good night, and I'll see everybody in the morning.